My supervisor is Dr. Mikola Maximenko, and I want to present you my master thesis work that is called Replica Exchange for Multiple Environment Reinforcement Learning. Here, the contents of my presentation. We first will go through the brief introduction to reinforcement learning. We will state the problem that we are facing, that is basically exploration-exploitation dilemma. We'll review some related work that we are using as a foundation for our work. Then we will look at the solution, evaluation. We will draw some conclusions and review the future work, and we will look at the comments from the review. So, a brief introduction to reinforcement learning. Basically, reinforcement learning consists of two main parts. We have the agent and the environment. We can control only the agent, and because of that, we are training the agent to optimize in the way that we need. The key concept here is that we have the state that we are observing from the environment, we have the reward that we are obtaining from the environment that we want to maximize. And we can act with the environment by a different set of actions. Usually, any reinforcement learning environment is described as a market decision process. Basic concept here is that we have set of states, we have set of actions, we have some transitions with different probabilities, and the main terms here that we're using in reinforcement learning is the return. That is a total sum of all the rewards that we can obtain during one iteration. We have the policy pie. The policy describes how the agent behaves, basically which actions the agent will choose for the obtained state. We have the state value function and action value function that is the value that is describing how good is the current state or how good is the action that we can take for the current state. We have action value function with the star that shows the best, the optimal action or value or state value function. And we have Bellman optimality equation that is basically a foundation for all reinforcement learning The main idea here is that to get the optimal value or Q function, we need to choose the actions that lead us to the best value at the next state. So now let's go to the problem that we are facing here. Exploration-exploitation dilemma. First, let's describe what is exploration and what is exploitation. In the reinforcement learning, the exploitation means that we act in the behavior to reuse the previous knowledge and to act the best in the way that agent already knows. Basically, it means that it will always choose the best actions with the knowledge that it already has. It will not try any new actions here. And exploration means that the agent will choose some random action or with some specified behavior action that will lead to obtaining new combination of action and state pair. And here at the picture, we can see some small illustration of that. We can see like the agent should both explore to find the best place of the behavior, and it should exploit to optimize it. There are different approaches to face this problem, like the agent-based approach, like epsilon greedy, which gives us some epsilon probability to choose random action or best action. We have in the agent we have the head of the neural network that is using softmax function to have the probabilities for the actions. It also gives us the possibility to explore or exploit with some probability. For some agents like advantage actor critic, we have entropy loss that we want to maximize, and in that way we want to explore the environment. We have some different techniques like regularization, dropout, or adding noise to basically generalize better the environment and in that way to explore it better. And why we decided to choose this problem? Because reinforcement learning is very non-stationary problem in the way that it highly depends on the initial state of the agent. And when we are running results, when we are running experiments, we always obtain different results because of its non-stationarity. And if we can solve this problem in the optimal way, we will always have the best possible results for the given setup of agent and environment, and they will be stable. So we reviewed different papers. Here I want to focus on the three main papers that we are using as a foundation for current work. First one is assessing generalization in deep reinforcement learning. What they did, they have added the noise as environment characteristics. They are changing the observing state of the agent, and they empirically proved that this approach improves generalization abilities of the agent. Second one is the recent research made by DeepMind called population-based training of neural networks. They're focusing on optimizing hyperparameters. They're using multi-agent setup to train in parallel. And population-based training is basically kind of genetic algorithm. The main idea there is that they're copying the agent that has the best results, and they are creating random agents to explore the environment. And the third one, it is not reinforcement learning based, but it still highly correlates with our solution. It's called training deep neural networks by optimizing over non-local path in hyperparameter space. It's also focused on optimizing hyperparameters. They also use noise. They're using the statement that noise flattens the loss function, and in that way the model can explore better the hyperparameter space. They're using multimodal setup that is training on parallel, and they're using Metropolis-Hastings exchange rule to exchange the model's hyperparameters during the time to efficiently sample from the hyperparameter space and obtain the best results. So what is our solution here? As I said, we are based on the mentioned related works. First of all, we are also adding the noise here. The mentioned paper is using sun-blazed environment wrapper for adding noise. We implemented our own noise on the top of OpenAI gym environment. The noise here is multiplicative, and X here is the noise basically, and it is sampled from the Gaussian distribution with mean equals 1 and standard deviation that equals the beta, where beta is a parameter of the specific environment. We are also using multi-agent setup here. Basically, we train multiple agents at the same time. Each agent has its own environment. These environments are the same environment with only difference in noise. So for the first agent, the noise is 0. Second agent, it's increased by some delta parameter, and so on until the last one. We are also using Metropolis hosting exchange rule here to exchange the environments for the agents. We adapted this rule for the reinforcement learning setup. Here, what are we using to make this exchange? First of all, it's the noise of the environment and the recent score of the agent for the last some number of iterations. And basically, it means that we will always, with probability equals 1, we will always exchange the environments for the agents if the agent with higher noise has higher score. It means that that this agent has found some better local optimum, and the agent with lower noise should exploit this area. And otherwise, we have some probability that is scaled by the hyperparameter delta that we can tune to find the best exchange rate that we need here. For our solution, we have stated two hypotheses. First one is that noise improves exploration, and second one that Metropolis hostings replica exchange improves RL training. By improving here, we are meaning that we will always we will efficiently explore the environment, and we will always find the best setup for the given agent and environment, and we'll have stable results. To make this research, we've built the research pipeline. So what you can see here, the core component here is noise learning model. It is using the agents. Here for agents, we choose GQN and advantage actor critic agent. And for environment, we've choose the Carpol environment from OpenAI, and we have our own wrapper on top of it to add noise. In the noise learning model, we're train those agents in parallel, and after some number of iterations, we are exchanging them by the described rule. And we store these results on the file system so we can analyze them further. Basically, here we can train different setups. We can train DKN agent with different exchange type. We can train A2C agent with different exchange types. We can have a lot of results, so then we can aggregate them and obtain the statistically correct results. And noise learning, for noise learning, we've implemented 3 types of exchange, so we can compare them. First one is no exchange. It means that agents will just train in parallel with their own noise level. A random exchange, it's just some random exchange with some probability between the agents. And smart exchange is Metropolis hostings exchange. And here we can see the results that we've obtained. This results is the aggregation on 10 iterations of the noise learning. Here we can see the results of A2C agent with no exchange. So here we can see, for example, at the distance plot, the distance here is the analogy from the physics for diffusion. We calculated the distance in the way that we are computing Euclidean distance between the weights of the neural network for the given iteration and the initial iteration. And what we can see here is that at the beginning, higher noise slows down the learning procedure, and same we can see here. But after some period of time, it improves exploration. We can see that this line for the higher noise is getting on top of other ones. Here we can see some results for the training procedure. And after the 5,000 iterations of training, to compare the results, we ran the play phase, where we just take one environment without any noise, and we play 500 iterations on them for each agent that we obtained at the end. And we can see that stable results obtained only agent with higher noise. The agent with the lower noise have good results, but they have big drops here, which means that most probable they have overfitted on some states that they observed. So next one, we have random exchange here to compare. We can see that now distances are combined for all noises into one line, we can say. The training score is much more volatile because of the exchanges. We can see some drops here that we didn't observe previously. And the play score is a little bit more stable because each agent had the possibility to train in the environment with bigger noise. And for smart exchange, we see a similar picture for distances. We can see that during training period, the results are much more stable, and we have almost 500 score. And during the play phase, the results are also a little bit more stable than during random exchange and no exchange. I will just say a little about DQN. For DQN, we didn't put much effort here. We didn't have enough time for it to optimize the hyperparameters. And because of that, we've obtained the inverse picture for the distance here. So basically, our DQN that we've implemented couldn't handle the big amount of noise and had some decent results without noise. So these results are interesting, but they need more experiments and more research here. And going to conclusions, just to reiterate on the hypothesis that noise improves exploration, I want to say that we had some trend with A2C. We saw that after big period of time, after 2,000 iterations, the noise started to improve. The exploration started to improve with higher noise. And similarly to the second hypothesis, we see that with smart exchange, we have a little bit higher score and with much more stable results. For DQN, as I said here, we don't have enough results right now to have some meaningful conclusion. We can see that we have some inverse picture for noise, and we need to have more experiments on that one. For the future work, here I want to say that we want to research the environment with higher complexity. Basically, we want to see if higher complexity will have higher trend on improving exploration with higher noise. we want to take a look at different noise type. Basically here we used noise as environment characteristic. We can also try different noise like mentioned dropout or regularization. We want to find a way to compare exploration abilities because here we have noise that we've implemented. Should I finish? Okay, so we have noise that we've implemented that improves exploration in one way, and we have agents that has its own techniques to improve exploration, and we want to find a way to compare them and to find which one dominates in what way. We want to find the way to measure the exploration potential of the environment. The Carpol environment that we've observed here has, we believe that it has small exploration potential because of its complexity, and we want to try on different environments. And the last one here is we want to parallelize training because this approach has a good perspective of parallelizing because of the multiple agents. Why we didn't do it right here? Because the environment was pretty simple and the agents were small, so parallelizing them would not have such benefits. And I have some review discussion here. Should I go with it now if I have time?
So yes, please.
I want to say thank you for the reviewer because we don't want to stop on our current research with Mykola. We want to continue, and this feedback is very helpful for us. First, I tried to make the comments much shorter because the comments are have a lot of details in the original review. So first one comment is that there is no reason to have Bellman's equation in this work in the chapter 1. We're not agree with exactly this statement because we think that Bellman's equation is a foundation of all reinforcement learning approaches, but we agree that the way that we've introduced Bellman's equation is not explained well. So this is the drawback of the storytelling of the first chapter. Second comment is that equation on page 8 lacks any explanation. It's the page about related work. I mentioned one equation there, and here I totally agree. I should have provided more context there so that equation would be more meaningful or remove the formula at all from there.
Excuse me, are there some specific recommendations, or just some so concrete?
There are more.
Can you jump into more?
Yeah, so.
Technical, yeah, not just technical.
Yeah, so they're like this one, why multiplicative noise was added. So.
But he knows the paid points. He knows the paid points. That would be more general.
Should I go further or stop here?
Perhaps we'll remove this discussion a little bit later. So
okay.
We'll stop right now, and we may proceed with questions and answers. Yeah. Questions, please?
Yeah. Can you show us the page where you quote cite the previous work?
Do you mean related work page? This one or?
Yes.
Yes.
You know, when you cite the work has always some authors, so it's not just title. You just gave us the title of the page.
Yeah,
no authors mentioned.
I tried to explain authors in words. Yes.
Well, I missed it. I didn't mention. Okay,
mentioned and they're cited in the.
Yeah, but still, yeah. And also, I would disagree that one can prove anything empirically. It's empirical, it's not a proof. your work is theoretical. I mean, you try to develop some model which would improve upon the existing approaches. Yes, and then to me,
opportunistic approach.
Yeah.
So I don't really have enough expressive power to prove the regular state theoretically. Therefore, I do some experiments.
okay, they can support the hypothesis, but not
Yes,
prove it.
Yes.
they may support, but you cannot do all every experiment first
Sure.
fully prove your statement.
Yes.
That's
So
why.
the problem. Sorry.
Yeah. And then another question is, you only tested your approach on these chosen environment particles.
Yes, right here it was only park-pole. We want to go further and try different environments with different complexities as well.
And do you believe that the approach would be as successful for other settings as well? What do you make? What makes you believe?
We believe in this approach because we are using the Metropolis Hastings exchange, and it is based on the detailed balance, which is already proven that it guarantees the efficient sampling from the space that we are exploring. So in that way, if we will have big enough amount of iterations of training, we will always find the we will always explore the whole space to find the optimal solution. So like this foundation here gives us this let's call it hope that it will also work on the environments with higher complexity as well.
So can you then specify what is your own
Contribution?
Yes, to this.
Yes, my contribution here is that first of all we've built the research pipeline to test our solution. And second one is that we've applied this exchange rule to the reinforcement learning. I didn't find any other paper who also tried this approach here. So that's our contribution on the direction of research in that way in reinforcement learning.
So you mean that Metropolis Hastings exchange was proposed by you? Or it was
No. It wasn't proposed by me, but we used this exchange in the reinforcement learning setup. It wasn't used in reinforcement learning before.
Where was it used?
In a lot of different places, like in chemicals for molecules. I'm not very experienced in that direction. Also, here.
Could this return back, sorry for the interfering, to the Metropolis Hastings?
Yes.
What does this formula specify? The exchange of what?
For our solution, it.
I mean, in the original paper where you have taken the formula.
We've used this. We've based on the work made in this paper. They used it also in adapted their own way, and the original
exchange between autonomous entities in some state, in some environment, wasn't it?
What again, please? I didn't hear the start one.
In that paper where you picked the formula,
yes.
Did they use this formula to specify the information exchange between some autonomous entities?
They specified the exchange between the hyperparameters of the model.
How dare hyperparameters exchange between themselves?
No, we have different models.
Different models.
Yes.
So autonomous programmatic entities that exchange information. What's the difference between your model and their model?
Here it's hyperparameter space, as I already mentioned, and in our solution, it's we can call it reward function landscape or space that is based on the state or actions, and actions are based on the weights of the model. So, like, this is a different.
Let's think for a second that reward is one of the hyperparameters. Would you mind that?
What again?
Reward is one of the hyperparameters. Would you agree with that?
Reward is one of the hyperparameters.
Or not?
I don't think so. Reward is
in machine learning model. Well, it's sort of a mirror function for a loss. And the loss function is one of the parameters of the machine learning model, isn't it?
Reward function is a property of the environment, and we can describe it in different ways that we want to optimize. Okay. In the reinforcement learning.
Any more questions?
Yeah, I do have. So, what is your problem statement?
Exploration exploitation dilemma, but it's like it's on more high level overview. It's about obtaining better and stable results every
Can you state
experiment.
one sentence? So, what is your problem statement? And your answer is?
Find the optimal balance between exploration and exploitation. Probably.
Quite broad, and you need to specify.
Did you achieve? Did you find the optimal balance between these?
We don't have any conclusions about optimal balance here, but we did have a little improvement on the training of the agents itself with their own ability to exploit and explore.
Improvement
compared to the case that they don't have any exchanges or random exchanges, for example.
So what is this smart exchange? Can you repeat, please?
Smart exchange, yes. So we have multiple agents and multiple environments. Each agent is trained on its own environment with its own level of noise. And after some number of iterations, for example, 30, we are looking at the noises of the environments for the specific agents, and we are looking at their recent scores. And we are comparing them using the formula I mentioned here. And we are obtaining the probability if we need to 100% exchange the environments for the agents. So basically, if we exchange them, then one agent will start further training on the environment with the noise from another environment.
So what is X?
Little X.
X here, yeah, it's here.
And L?
L is reward, obtained reward, yes.
Okay, and you mentioned this after 30 epochs, right? You may.
Yes, for example, right, in our approach, we used 30, yes. It's arbitrarily chosen parameter. We also want to tune it and to find probably the better results.
Did you try to play with different? It's another hyperparameter.
Yes, it's a hyperparameter of our solution. We have also like few hyperparameters I mentioned in cases here as well.
But did you try different?
For these experiments, we didn't try different. Like we thought that 30 iterations for the cardpole environment is enough to obtain some insights and to exchange.
What was the ground behind this 30?
It's knowledge about the cardpole environment, and that's all.
And
what this ST mean?
It's a state of the environment at the specific timestamp.
Yeah, but if
What do you know as a state?
State is like some matrix or vector of values, and I multiply each value by some random variable x.
and can multiply by a negative number.
Yes, in that one there were such cases as well.
So it's not a problem.
No.
I have several questions. I have several simple questions, several philosophical questions. Simple questions are just to ensure that we're on the same page. I mean, terminology. The first simple question: will you please denote an agent?
Agent is a software, I would say, software that can interact with environment and can train based on the given task to optimize some function.
What do you mean by in the interaction?
Choose different actions and apply them on the environment.
Have you looked into the professional literature on software agents? There's nothing in the related work about that. And several properties, those software entities called agents, which are specified, well, I would say 2 decades ago. You have to follow the mainstream of that. Could you please denote a behavior? Mention behaviors.
Yes, I mentioned it in the statement about policy. So what did I mention? I said that the agent policy is its behavior, how he interacts with the environment. So basically, which action he will choose for the given state. So it's a policy. I just used the word behavior as an analogy.
The choice of an action is not part of the interaction. But this is my interpretation. What did you mean by, I'm quoting, the place of the behavior? That behavior is especially dispersed in the environment or something else. I don't remember the slide where, by the way, we can't see the slide numbers on your presentation, which is, therefore it's hard to refer to. On one of the slides at the beginning of the talk, you mentioned the place of the behavior that was positive.
Yeah, probably just was somewhere here. Yeah.
Perhaps. So where is the place for a behavior?
I think the place word wasn't correct here.
It wasn't correct. Okay. Please denote an environment.
Environment. I also didn't look at some.
I know that. We have checked that already. No more excuses. Just explain how do you see the denotation of an environment in your context,
I try to describe environment here. So,
yeah.
As I said, environment is it could be a software, or we can also transfer it to some real world environments. So, environment is like, I would say it's a set of states that
Whose states?
environment has states.
Environment has states.
Yes.
How do the states change?
They're changing by itself with some probability of transition from one state to another. and they could also change because of the action taken by some agent.
So you think that an environment has states, not an agent?
Yes.
And there's this markup process that you have shown you on the slides. It abstracts the environment or an agent in the environment?
This one is the environment.
The environment. So the actions also belong to the actions A1, A0.
Yes, they also belong to
They
environment.
also belong to environment.
Right. The set of possible actions.
Right. Sorry. Right.
Agent decides each action.
No. All the stuff, all the situations that may happen in the universe lie in the environment. So agents are just blind things that explore and blow on the actions if they're not lucky. Okay. That is a very interesting question. In your work, are agents autonomous or cooperative or competitive or adversarial?
They're autonomous.
Autonomous. Well, how dare they can communicate if they are autonomous? If they're autonomous, they're autonomous. If they communicate, they are either cooperative or competitive, depending on their beliefs and intentions. I'm sorry.
Yes, so
And game settings, not play, game setting.
we can say it, I believe, in two ways. Like, they are autonomous, and we have something on top of them, which we call noise learning, for example, that can decide how to exchange the environments where they behave, but they can not know anything about it. And second one, about the noise learning that exchanges the environments. They just act on the environment and get different states, and that's all.
An agent, if understood in a traditional way, is an entity which is situated in the environment and has the possibility to perceive the environment. It has sensors.
Yes.
Perceive the environment and perceive information from the environment. And this is the way to learn.
Yes.
In reinforcement learning also. If you use agent-based setup in the reinforcement learning task. So. Well, this question will be answered. You have a multi-agent setup. Are the environments that you showed on your solution page overlap?
What do you mean by overlap?
Environments may overlap spatially, temporally, functionally, situationally, or actionally, depending on is there any overlap, intersection between the sets? I mean, if you put it on an abstract level. There is environment 1, environment 2, and there's a common part between them.
Like, they don't have any cooperation. So I would say
environments are just environments, they do not cooperate.
Yes. It's just like duplicated instance of the same environment with different noise
so
level.
All the agents are situated in the same environment.
Yes, it's the same environment with different noise level. Yes.
In different experiments.
What do you mean different?
In different simulations, you just add different level of noises.
No, it's one simulation, and I have at the same time in parallel trained multiple agents on multiple environments with different level of noises. And
so
next experiment is...
The only difference is the level of noise.
In the environments, yes.
Okay. You mentioned already that agents communicate. I do not really understand why. What do the agents communicate? Which pieces of it? convention do they communicate with each other?
That's why I was trying to say that, in my understanding, that they're autonomous because they don't communicate
But you mentioned further that they communicate.
We have the model on top of the agents that is exchanging the environments for the agents, but agents don't interact with each other.
Okay.
Maybe you wanted to say that. How can you exchange environment if the agent is in some state at some moment? How can you?
Like
how can you just
the agent is we can say that it's in environment, but like in fact it's just a separate let's call it instance that interacts with it,
and we change the information and everything they have learned to improve performance, or I don't understand that. There's change environment and
we can say that in that way there.
Excuse me. Yeah, you said that environments are the same, so they are just copies.
Yes.
Does it matter?
Yeah, in the simulations, they just try the agents at different level of noises.
Yes.
In the same environment.
Yes.
So why say that the environment is
They interchange are
Sure. And the idea of actually exchanging the agent is like that. The general problem is not that much exploration of implementation, it's actually generalization of the agent to different environments. So usually that's actually connected to exploration. And the ability of the agent to train on multiple environments at the same time, it's actually like allows to improve. And usually people do it in random. And in this particular work, we do it in more elaborated way. So agent knows when to switch environment to actually improve its ability to generalize that.
So the information is shared to all agents based on the common information. Yeah.
So you have this model on top of that, which actually accumulates information from the agents and how they train within the environment, and then actually governs how they.
What is the communication model? Is it a blackboard type model, or what's that? What is the communication model between the agents? If they know, if they share, is it a blackboard? So the model which is on top is used like a communication blackboard.
It's kind of a master nodes which assigns which environments agents should learn at this moment.
Oh. That becomes even more interesting. The problem is that it's not described in the way. Yeah, we're on the solution page. What do these bidirectional arrows mean on your figure between the environments and between the environments and models?
Between the
environment
and model, it means that like the agent interacts with the environment, and between the environments, it means that we are exchanging them. Basically, what we've already said, that we don't have, like, probably I should also illustrate here the so-called model on the top that have this knowledge how to exchange them.
You just have to explain what is the meaning of an error. And the errors should be different for different meanings. Exchange is not the same as interaction, but errors are the same. To confuse it, sorry.
Okay.
One more thing. After looking into your thesis and after listening to your presentation, I'm puzzled about one question. I'm looking at your solution presentation and start understanding that it might be a problem set. Is that so? Is this solution page your problem setting?
What do you mean? Like solution page problem set?
Okay, I will try to use more simple words. When you start writing your thesis, you first try to find a research gap, right? There are several solutions within this problem domain, and there are gaps. These parts of the problem are not solved. And then you focus your work on narrowing one of the gaps, right? And then you state the problem in the context of this gap, right?
Yes.
I didn't find it there. So now I'm looking here and do see that this perhaps is the setting of your problem, because the gap is the influence of the noise. Is it?
I would say that influence of the noise, that was something that we might actually explore in his one of the bachelor works. So he already looked on how noise
Machine learning project.
actually affects the training of the agents.
Okay. So what is the contribution of this work?
Excuse me?
What is the contribution of this work? Because he said in his talk that his contribution is to study how does noise affects the learning process.
That was more elaborated in this work in more details.
Okay.
That's one thing. Another thing, maybe you can just comment by particular statements to your contributions.
Yeah, I already, that was the question, one of the questions. I said that we've researched the approach of using Metropolis Hastings Exchange in the reinforcement learning setup. So basically, what we were just talking about, that noise improves generalization, is only one.
You see why Metropolis has.
Yes.
You should have put him in front at the very beginning.
I may just comment. So
Yes.
I think the very valuable contribution of Dmitri is that he built this really nice research framework where he now can run a lot of experiments, evaluate different hypotheses, different models of noise, different models of agents.
So you now may play with the simple environments and try to fine-tune the strategy.
So now
Based on different approaches, like really learning, like injecting some noises, like regularization, like this.
Yes.
But can I just make a bit precise back to this solution? So this schema, I would say, a model was proposed to you, and then you work within this.
Yes, when we met with Mikola, he proposed that they already made this research.
So they have already this kind of idea.
They used this same approach in their paper of optimizing hyperparameters in deep learning.
See why you need to have authors to code them properly. But back to the schema. So you had it beforehand, and then you work within. That's why your hypothesis belongs to this idea, but not goes advance. So you state your hypothesis already at the base of this solution, and you work within this solution. Correct?
This is a generic mistake for everyone.
I mean, no, because this was your question.
Exactly. But it could be well generalized to all the things here. Yeah. Unfortunately. So did I understand you correctly? And this, correct me if I'm mistaken. So the contribution was to develop a research test bed to play with this step and optimize, fine-tune the learning strategy.
Well, the goal was actually to answer a lot of research questions, but to start with that, you not have to build the framework, and that was quite a lot of work.
So it looks like a nice test bed, and that could be a real valuable master work.
Exactly. So then, and there was really little time for particular experiments. So that's why the experiments might look like very simple right now and maybe not providing too much details. But there is a lot, so like another valuable contribution which I really like in this diploma is that you actually outline a lot of different future directions which can be explored now. And within this framework, this could be our test. So these initial experiments allowed him to identify the future directions. In particular,
This is excellent if he were emeritus. Yeah? But unfortunately, for a master project, it should be an accomplished work. So we have to assess the accomplishment. I'm sorry to say. Okay. One more question. Out of curiosity, what's the rationale for this play phase you mentioned in the slides? Experiment. What's the rationale? Why do you need this play phase? What is the play?
I wanted to somehow compare the results that we obtained. So, like, just having this plot of how the agents train didn't give us enough insights to have some starting conclusions for the future research. And because of that, I also tried to add this play phase to actually try to compare what is the agent's performance at the end of the training.
So this is just the final training phase.
It's after the training.
So the play phase and the training phase are the same or different?
They're different. During training phase, the agents are optimizing their parameters, like for deep learning, it's weights. And for play phase, they're only choosing the actions. They don't make any learning. Yes.
On test data.
Let's say in that way. Yes.
Okay. What else? Ooh, still that's it. Why was the project planned so badly? You confessed that you had no time, and therefore spent little effort for the GQN.
Yes.
Why you planned your project so badly?
Our main idea is that this research will continue to work with it for getting more results and probably publish somewhere this work. So that's like only some intermediate step here.
This is a recommendation for you and for all those who are still sitting here. If you are going to confess not bad things in your work, just turn this disaster into an opportunity. Never say, I didn't do that and I had nothing to show, but it was planned. That means that the work did not reach all its goals. Will be down scored for that. That's a warning. Anyone else? The next question is a straightforward consequence of the previous. Did the project reach all its goals? What were the goals of the project, and could you please show the checklist?
We didn't set up some specific and detailed goals.
It was just fun.
No. Like, we had more abstract goal of making the research of this approach, if this works and how it works. And we've obtained some trends, but we currently don't have enough insights to say that if we acknowledge the hypothesis or not. So we still need more further experiments and work.
Okay, so, and finally, a philosophical question, as promised, about the impact, potential impact. What's the reason to study noise?
I'm just trying to understand what do you mean by philosophical question, because
for public good, is it really reasonable, rational, bring some extra utility, super additive to study noise in these settings? I mean, in terms of in the context of reinforcement learning tasks, practical.
I can say that in terms of reinforcement learning, as I already said, noise improves generalization abilities of the agent. He doesn't overfeed. So
in terms of overfit.
yes, it's one of them.
That was the result that you got after the simulations, after you done the experiments. But,
That result
before
will.
doing that, when you were thinking about the unsolved problem, what was the reason for you to choose the focus on noise?
We already knew that noise, like
How did you know?
my previous work on the machine learning project,
Okay,
and
that was incremental, yeah. I almost forget about that. Sorry. Yeah, you answered this philosophical question. Thank you, Anthony. I'm
I
done.
can just comment. So
Yeah.
generally, the idea, the overall idea is to explore environment with complexity. So noise is just a toy and model of how to introduce complexity to the environment. So you generally can think about applying that to environmental complexity. If you have a different level of complexity in the environment, we also can say that these are different level of temperature. And then you can allow agent to train in the low complexity environment, then increase complexity, then without additional divorce, reduce complexity and so on. So introduce such paths.
Yeah, one of the important types of injection complexity. Could be regular complexity.
And noise is literally a good example, like some controls.
Okay, fine. That's why I'm saying that having a nice test bed for the further research. That should be put in the title. Not like that. Sorry to say. I'm done. Any more questions, guys? Okay. Thank you very much. I'm sorry for choosing you as a victim. You did all best to